All right, we're going to talk today about converting equations from polar form to rectangular form and vice versa. Okay, but in order to do that, we need to recall what our pillars of polars are. Right, we have four pillars. Let's see, can we remember? Well, the first one is x equals r cosine theta. The second one is y equals r sine theta. The third one is r, I should put these as little asterisks here. R equals the square root of x squared plus y squared. And the last pillar is that tangent of theta is equal to y over x. And in the last video we went over, or the last conversation we had, we went over where these came from. And just a reminder, they come from our knowledge of the circle of radius r, where this is x and this is y. We also know that these components are r cosine theta, r sine theta, right? And then it would be x squared plus y squared equals r squared, because this is r. And that's where these equations came from. And of course, they rotate an angle theta. All right, so the first equation that we're going to convert from polar form to rectangular form is a pretty easy one, and it's r equals 3. Well, what do we know about r? Well, if we go to our pillars of polars, we see right away that r is equal to the square root of, so I can convert this to the square root of x squared plus y squared equals 3, and then I can square both sides, and I get x squared plus y squared equals 9. And there we go, there's our conversion. And we all know this in rectangular form is a circle centered at the origin with radius 3, and this in polar form is a circle with radius 3. Okay. All right, what about theta equals pi over 3? Well, I notice that I have an equation with my pillars of polars here where tangent of theta equals y over x. So what I'm going to do here is take the tangent of both sides. So if I do that, I get tangent of theta equals the tangent of pi over 3. Right, if I take the tangent of both sides here. What I do to one side, I can do to the other. All right, but what is tangent of theta equal in polars? Well, we can see that tangent of theta is y over x. So this is y over x equals the tangent of pi over 3. Well, if we do another recall here, the tangents in the first quadrant, if you recall, are 0, root 3 over 3, 1, root 3, and undefined here. Okay, so tangent of pi over 3 is root 3. Okay, and so I'm going to solve this for y and get y equals root 3 times x. And so this is, right, well, this was a circle, and this is a line. Okay, now I like to show on Desmos what that looks like, and I happen to have that up right here. So r equals 3. That's the first one. See, that's a circle with radius 3, because you go out radially 3. And there is no theta in our equation, so theta can be anything. So that's why that's a circle. Okay. And the last time I did this, I realized that we can't put theta equals, but I can do y equals square root 3 times x, and you'll see that we get a line where theta is always pi over 3. Okay, so that works. All right, so let's do the next one here. I have r equals secant theta. Well, secant, I don't have a pillar or polar that is a secant, but I do know that secant is equal to something. If you recall, back in the day when we did trig first semester, we know that r equals, the secant is 1 over cosine. So I can change that secant to 1 over cosine. And then I can multiply both sides by cosine. and I get r cosine theta equals 1. Now when I get r equals cosine theta equals 1, well, if I go to my pillars of polars, I can go up here and I say, well, wait a minute, x equals r cosine theta. So I can put an x where I see r cosine theta, and I get x equals 1. So this is a vertical line at x equals 1. So let's look at Desmos and see if that agrees. So I'm going to say r equals secant of theta. And as you can see, I'm going to get rid of these real quick. As you can see that we get a line here at x equals 1, which is pretty cool. Okay. All right, let's move along to the next one. From your notes, the next one here is r equals 2 cosine theta. Now in this case, what I do here is a little bit different strategy here. I'm going to multiply everything by r. And when I do that, I'm going to get r squared equals, because I'm going to put both sides by r, 2r cosine theta. Okay? Now, that's helpful. Why? Well, because I know now that this is r cosine theta, and I know that that is x. So I get r squared. Well, actually, let's try this a different way, because I think it'll be a little bit more intuitive if we do it the other way. So give me a second. Let's try again. I mean, you can do it this way, but I just had a better thought. Okay, so we're going to start with r equals cosine theta, because I think 2 cosine theta, most people are going to be better with direct substitution than introducing multiplying. And that's why I've changed my tune here a little bit. Now, what do I mean by that? I mean, do we know what r is? But yes, we do, but I'll hold off on that. But what is cosine equal? If you go back to the pillars of polars, what do we know? We know that the x equals r cosine theta, but cosine theta, if I solve for that, equals x over r. So this is kind of a corollary. Okay, so I'm going to plug in r equals 2 times x over r. Okay, and then when I do that, because cosine theta is equal to x over r, I'm going to multiply both sides by r now to get rid of that denominator, and I get r squared equals 2x. Well, that's great, but I still have an r squared in my equation. But what do we know r equals? Well, we know r equals the square root of x squared plus y squared, and I know then r squared is going to be x squared plus y squared. So where I see r squared, I can put, oops, I forgot the square here, x squared plus y squared equals 2x. Now, I'm going to put this in graphing form, so I'm going to subtract the 2x over. So we're going to get x squared plus or minus 2x plus something, right? Plus y squared equals 0. I'm going to complete the square. Oh, I hear moaning from the background here. Completing the square. Oh no, completing the square. Yeah, we got to remember how to complete the square. What happens here is I take half of this term here, -2, and square it. So half of -2 is 1, and I square it and I get 1. And so I have to add 1 on this side too, because what I add to this side, I have to add to this side to make the equation still equal. Now this is a perfect square, which is x minus 2 quantity, or I'm sorry, x minus 1. Been a long day. X minus 1 quantity squared plus y squared equals 1. Well, now we recognize this, don't we? Well, yes, we do. This is a circle with radius of 1, centered where? Centered at, I heard it from the back, 1, 0, and you would be correct. Okay, so let's graph it. on Desmos. Oops, I need to be able to see it. X squared, x minus 1 quantity squared plus y squared equals 1. All right, here we go. Get rid of this one here. And we're going to go r equals 2 cosine, oops, helps if I can spell, theta. There it is. Do you see how that's our circle there, centered at 1, 0? And I'm going to prove it to you by writing the rectangular form. This would be x minus 1 quantity squared, that's parabola part, plus y squared, oops, helps if I type a plus. Where's Robbie when I need him, right? Equals 1. And JP. You guys are my drivers. Anyway, here we go. So you see how these curves are the exact same in rectangular coordinates, and you can see the purple there, and in polar coordinates. Okay, so what's the strategy? The strategy is to find a way to eliminate the r's and the thetas by looking at our 4 pillars of polars and doing some substitution to get into the better sets of equations, okay? All right, well, what about going the other direction? I'm going to fold this so it looks better. Going the other direction, from rectangular to polar. Well, let's recall again, we know that x equals r cosine theta, the pillars of polars, y equals r sine theta, r equals the square root of x squared plus y squared, and tangent of theta is equal to y over x. Okay, so here we go. Now we're going to go the other direction, which maybe is easier. I don't know. You guys will have to decide once you do a couple of them. All right. This is a pretty straightforward transformation of this equation, because what does x equal? Using the pillars of the polars, x equals r cosine theta equals 5. Now, when we're trying to find an equation in polar form, we typically like to have it as an r equals a function of theta, or theta equals a constant. Those are the two forms that we want. Okay, so I got to solve for r here. So solving for r, I get r equals 5 over cosine theta. But what is 1 over cosine theta? Well, that's just secant, so this would be 5 secant theta. And of course, we know that this is a vertical line at x equals 5, and so anything that has a secant over here to the right, you're going to hopefully start recognizing that I'm going to type x equals 5, and then I'm going to type in r equals 5 times the secant of theta, if I can spell. And you can see if I scoot over here, and I'll make one dashed. Sadly, they don't have yellow, and I have to use Georgia color. That's annoying. Well, I'll live through it. But anyway, so do you see how x equals 5 and r equals 5 secant theta are equivalent? Good. All right, let's do another one. Here we go. We have 3x plus 4y equals 2. Well, this is a line in rectangular coordinates. And so we're going to figure out how to write this line in polar coordinates. So what am I going to do? I'm going to directly substitute what x and y are. Ha ha ha, get the pun? X and y are. All right, so this is going to be 3 times what x is, which is r cosine theta, plus 4 times r sine theta equals 2. And remember, my goal is to get r as a function of theta. So I got to get all the thetas on this side and the r all by itself over here. It's like solving for y, except for solving for r. Okay, so I notice that I have an r in both of these expressions. So I'm going to factor out an r. So I'm going to factor out an r, and I get 3 cosine theta plus 4 sine theta equals 2. So r equals 2 divided by 3 cosine theta, because I'm going to divide both sides by this, plus 4 sine theta. Okay, there we go. There's our polar form of the equation of the line. 3x plus 4y equals 2. All right, so let's see if it works. I'm going to try to avoid those shorts of colors if I can. So it's going to be 3x plus 4y equals 2. There's my equation of the line. And I'm going to do it in polar form, which is r equals 2 divided by 3 cosine. And she spelled theta right this time. Yay, she did. Plus 4 sine 2 times in a row. Yes, I did. All right, and you can see here that they are the same line in rectangular form and in polar form. All right, now let's do a challenger. Here we go. Here's a challenger. Oh boy. Well, this is a circle, right? We know that. It's centered at 3, 2 and has a radius of the square root of 13. Now, what I'm going to do here is I'm going to expand this first. Why do I expand it? Well, I expand it because I know that, you know, x squared plus y squared is equal to r squared, right? I mean, so this is kind of a corollary. I know that. So, and I know if I expand this, I'm going to get an x squared and a y squared. So that's why we're going to expand it. So let's do that. We're going to get x squared minus 6x plus 9, if I expand that square, plus y squared minus 4y plus 4, y's look the same, equals 13. All right, now I'm going to try to get r equals. So I'm going to move these things together. So I'm going to get x squared plus y squared minus 6x minus 4y equals 13. Now I know this already is r squared, right? Because we already said that x squared plus y squared equals r squared. And what do I know about x? Well, I know x is equal to r cosine theta, and y is equal to r sine theta, and that equals 13. And now I notice that I have an expression where I have r's that an r I can factor out. So I'm going to factor out an r, and I get r minus 6 cosine theta minus 4 sine theta equals 13. And now I have an equation here that I'm going to, oh wait. What did I do? I forgot. I got to go back in time. Roll back the tape. Roll back the tape. I went ahead of myself here. So I'm going to move this 9 and this 4 over to the other side. So I get 13 minus 13. Sorry about that. I had it in mind. I was so excited to change the x plus y squared into r squared. I totally forgot that I had these constants here I got to get rid of. So I'm going to put that on the other side, and I get 0, which makes me more satisfied, because at the end here I have the 0 product property, because there is no such thing as a 13 product property, and I went and so I had to fix it. So yes, so the 13 minus 13 is 0, so I get 0 on this side. So I can say that r equals 0, or what else has to be true? R minus 6 cosine theta minus 4 sine theta has to equal 0. Okay, now r equals 0. Let's think about that. On the polar plane, if I'm doing my polar plane here, right? R equals 0. How far out radially would I go? Well, I wouldn't go out anywhere. Well, guess what? This is just the pole. So I look at that as an extraneous solution. Or what's a solution that's equal? It's because if I let x equal 0 and y equals 0, what happens here? I get 9 plus 4, which is 13. So this is part of the solution, but I need this part to give me the curve that I want to draw. So here we go. So this is going to be r equals 6 cosine theta, if I move this to the other side, plus 4 sine theta. So this right here is actually the circle. So let's see what I mean. Okay, what happens if I do r equals 0? Oops, it helps if I type in the right spot. R equals 0. Does it plot anything? Well, the answer is no, it doesn't plot anything because it's just the pole. All right. What about this one here? We say r equals 6 cosine theta, oops, close, plus 4, ooh, that's a cool looking curve, isn't it? Sine theta, I got to remember that. I can spell theta. Wow, this is pretty big, but we knew it was a circle, didn't we? Oop. Oh, we're having fun. All right. Well, I got to get my cursor off of there before I move over here. Yeah, so there we go. And then let's do the rectangular form to see if it matches. We get x minus 3 raised to the second plus y minus 2 raised to the second equals 13. And there it is. And, oh, gosh, I'm at Georgia colors again. So we're going to get rid of that. We're going to use orange. Yeah, there we go. And we'll do Halloween, right? Black and orange. Okay, so can you see now that those are equivalent conics? All right, so that gives you a little bit of a taste for converting equations from rectangular to polar and polar to rectangular form. So I apologize for the craziness here and not subtracting the 13 over from the other side. But anyway, we don't bother to graph this pole point. This is the circle and this is a circle, right, of radius root 13. So this is equivalent to this, and this is obviously being a circle, so is this. Circle is one of those cool words that looks weird when you spell it out. But anyway, so you guys have a great afternoon and have some fun playing around with that on the homework. And if you have any questions, email me, and I will do a quick little video and show you how to work a few if you need me to. So have a great day. Thanks.